Today we're talking about electric fields. This is still on your homework number 1. We didn't finish off the homework number 1 material last time. So what electric fields are is a way to think about charge interaction with in a very different way. And at first, you're going to wonder what's the point of it. Yes, it comes with some seeming advantages, but it also comes with some additional weirdness. So why would you want to do that? And we'll find ultimately that the reason why we do it is because it's incredibly computationally helpful. So here's how I'll introduce it. Let me say I have a charge. I'll call it capital Q and lowercase q. You'll see that there's a nice reason why I label them that way. And of course, they could either charge or repel, depending on whether they're plus or minus. Let's just, for the sake of argument, say that they're both plus. And so since they're like charges, they're going to repel, like so. And that's what we've been doing so far. We use Coulomb's law, and it can tell us the amount of the repulsion depending on how much the charges are and how far they are apart. But here's the thing that really bothers, if you really think about it, how do they know to repel each other? These things potentially can be far apart. Maybe there's something in between where they can't directly, quote-unquote, see each other, and yet they know to repel each other. This is the action at a distance kind of conundrum where it bothered people that how do the charges know about each other? They could be millions of miles apart. There could be whole planets in between them or whatnot, and yet they still know to repel each other. So, what do we do to get around this idea of action at a distance? So, action at a distance, it seems kind of strange. And so we move to the field approach, which sort of resolves it in some ways and sort of not in others. So what we do is we just shift a perspective. We imagine a different model for what's going on. This is what we imagine. This charge, big Q, it doesn't have any particular desire to, or it doesn't have any particular knowledge of the other charge. What it does is it just puts some kind of pervasive influence into the space everywhere around it. In fact, to the edge of the universe, which at this point, having no lack of any better way to draw it, I'll just draw as kind of some soup. And of course, later on, we'll draw it in a kind of a more informative, structured way. But for right now, we're imagining that this charge just simply puts some kind of influence into the space everywhere around it. That includes, by the way, the edge of the universe, because of course the Coulomb force is an inverse square law, and so it never really drops to 0 until you're infinitely far away. So this is our cause of, and what do we call this influence? We call it the electric field. Okay? So that's the part that's pretty hard to swallow in the sense that, well, what do you mean it puts something out into the emptiness of space everywhere to the edge of the universe? But if you can take that, on the effect side, it's quite straightforward. Because the effect is on little q, and we can say that little q doesn't have any knowledge of anything going on anywhere else. It's just simply reacting to the electric field where it is. So there's some kind of influence in the space, and it's sitting in that space, and it feels the effect. So it feels the local electric field at its own location. So it's much more palatable on the effect side than on the cause side. So, let me try to give you an analogy for what we're doing here. We're switching from the force picture to the field picture. The force picture is a picture of direct interaction. So for instance, let's imagine that this entire room, instead of it being a hard floor, let's imagine it was a mattress, okay? So if I started jumping up and down on the mattress, well, that mattress would, of course, have all sorts of vibrations going out, and you sitting in your desk on that mattress, your desk would start jiggling around, right? So if someone asks you, why is your desk jiggling around, you'd point to me and you'd say, well, that guy over there is jumping up and down on the mattress, that's why I'm feeling the effects. That would be like the force picture, this idea that we're directly talking, you consider me far away from you as the cause of what's happening to you. In the field perspective, imagine it's the exact same scenario except you put on a blindfold, okay? You put on a blindfold so you can't really see anything or anyone that's in the room. I start doing the same thing. I start jumping up and down on that mattress. If someone asks you, why is your desk jiggling around? You might be more liable to say, because the mattress underneath my desk is jiggling around, right? So you're thinking of it more locally, right? You're thinking of it as, the reason that what's happening to me is because of where I'm sitting. Because you don't ultimately know, is it me jumping around? Is it someone over there jumping around? Is there an earthquake? You don't have any idea what the reason is why you're jiggling around anymore. But you do know that the ultimate cause of why your desk is being lifted is because the mattress underneath your desk is vibrating, right? That's the field picture. It's about taking the idea of what's happening to you and making it local, right? Instead of blaming someone else somewhere very far away, you're turning it into a local thing. So hopefully that makes sense, except the analogy is far from perfect. When you're talking about a mattress, there's fabric and springs, things that can vibrate, right? What is out here? Nothing. This is completely empty space. There's no air, there's no matter, this is nothing. So what we choose to do is to think that there's an electric field that is present. There's something that can be present in absolute empty space, okay? So the analogy is not perfect because when we're talking about the floor of this room being a mattress, there's stuff to affect, right? But we're talking about completely empty space. And in fact, if you were to question me and say, hey, how do you know that there's an electric field here? Where there's nothing, it's absolute nothingness. And to which I would say, well, if you put a charge there, it'll feel a force. To which you say, well, how do you know the field was there before you put the particle there, right? Maybe the field came into being to affect the charge when you put the charge there. How can you say there's a field there before anything was put there to react? That's kind of like the old, you ever hear that if a tree falls in the forest and there's no one there to hear it, does it make a sound? Well, the answer in that case is yes, because there's still air and other things to vibrate, but this is a more apt situation. So we choose to think this, okay? We choose to think, for convenience's sake, that there's electric field everywhere, even places where there are nothing to be affected, because when we do put charges into this region, they immediately feel an effect, the force, and we choose to believe that the effect is from some underlying field that's everywhere, even where there is nothing to be affected, because when we do put a charge down, it is affected, right? So that's just a matter of perspective, okay? If you understand that, you understand the idea of a field, and it's really important to just get that basic idea, because otherwise you're going to be lost when you try to tackle some complex problems, okay? So that's the idea of a field. Now, I should mention, if big Q makes a field, and little q feels the effect of that with a force, of course we know that there's also an equal and opposite force, right? So could you say that little q makes its own field and big Q sits in that field? Absolutely. So it's always a mutual thing, right? We say that any charge can make a field of its own, and any other charge can feel an effect from that field, and that charge itself also makes a field, right? So the only place where you can get in trouble is where you have that a charge makes a field and then also feels that field back on itself. That doesn't make any sense, right? That's like a self-force. You can't exert a force on yourself. So remember that the electric field is the middleman between two particles, two charges. So big Q and little q both make fields, and both of them feel forces from the other's field, but never from your own field. That's like picking yourself up and carrying yourself out of the room. Okay, you can't do it. Okay. Now, my labeling scheme, capital Q and lowercase q, is just which way we care about it. So if I label something capital Q, that's kind of your hint that that's the things we want to be the causes of our fields. And when I label something little q, I want it to be the effect. Those are things that feel forces, okay? Even though everything goes exactly the other way too, right? All charges are, there's no special charges that only make fields and other special charges only feel fields. Everything goes the other way too. This is just my labeling scheme to give you a little sense of which way I care about the interaction, okay? So especially at first, I will try my best to label them in this way so that it's clear. What do we want to compute the field of? What do we want to calculate the force on, right? Does that make sense? Okay, so that's my labeling scheme. So, now that we kind of have that squared away, I want to start, of course, making this more quantitative. So let's use it for calculation. I'm going to start on the effects side. So that's basically the force. Actually, yeah, I'll go ahead and recopy this as needed. Right now, I want to kind of group it in some logical way, but for right now, this will be fine. This is my equation. And let me tell you what I'm writing here. First of all, sizes only, right? I just want numbers to pop out of this. Obviously, a force is a vector, but I'm just worried about the magnitudes. I'm not, direction will be taken care of separately. I'll do that later. So my two vector quantities, force is written without a vector hat. That means just the size of, always positive. Electric field is also a vector. I haven't quite shown you that yet, but I've certainly written it with that variable. But over here, it's written without the vector hat, so again, size of, so just a number. And then of course Q is not a vector, but it can be plus or minus, so I'm going to take the absolute value sign to make sure that's positive, right? I just want numbers here, no signs. Okay? So, what is this equation? This is the size of the electric field, at Q's location. Now, that can't be due to that charge itself. It's, of course, due to some other charge or even multiple charges in the region, right? The big Q's. But we're not worried about that yet. We're just assuming we know about the local conditions where little q is. If you take that and you multiply it by the amount of charge that's placed there, it will tell you the force on that charge due to local conditions. So this is the force on little q, or just I should say the size of the force. So it's a very handy formula. All you have to do is say what's the field there, what are you putting there, and it'll tell you how that thing is affected. Now that might not seem like much, but I do want to emphasize that this is a property of space. It's a property of the location. We say that it's there whether or not you choose to put anything there. That property exists at that location. When we supply something to put there, then this will tell us the force on that charge. So we could say it's a property that acts on a charge, right? You can't pull on nothing. There has to be something to pull on. You can't pull on empty space. So even though it's just a simple equation with 3 different variables, it allows us to take something that's true of the location, put something at that location, and it'll tell us about what happens to that thing we've put there. That's the essence of that equation, right? In fact, this allows us to, let's look at the units here. Well, force, what's the units of force? Newtons. What's the units of charge? Coulombs. So what must be the units of electric field in order for this to work out? Newtons over coulombs. That is the units of electric field. Electric field is measured are newtons per coulomb. That might be just having units to discuss might make it easier to state what an electric field is. The electric field states how many newtons of force are available at a location in space per coulomb that you place there. Okay? That's one way to think about what the electric field is telling you. It's telling you that at this location, there are so and so many newtons of force that will act on something if you place it there, and it's telling you how many newtons of the force are available per coulomb that you decide to place there. So let me give you an example. Okay? Let's say we somehow know, let's go back to our original diagram. I'm taking big Q completely out of there because I don't need to know about anything except the local conditions where little q sits. And let's say somehow I know that the magnitude, I'll bring in the direction later, but the magnitude of the electric field at this location is 10 newtons per coulomb. I guess I can take the charge out too. So just somehow at this location, the green blob that I was drawing there, the location in space, has this property. So now let's try bringing in various charges to that point and seeing how they get affected. Well, I guess we could start off with Q equals 0. How much force will that feel? 0. It feels no force. Maybe it's a particle with no charge overall, like a neutron, or maybe the reason why the charge is 0 at this location is because there's literally nothing there. Regardless, no electrical force will be experienced. Let's say we decide instead to put a 1 coulomb charge there. We put in our equation, 1 coulomb is what we put there, and the property of space is 10 newtons are available per coulomb. So how much force is that going to experience? 10 newtons, right? The coulombs cancel. That particular particle will experience this force of size 10 newtons. Let's swap it out with something else, 2 coulombs. So 2 coulombs placed at a location in space where 10 newtons of force are available per coulomb. How much force is that particle going to experience? What's that? 20. So there's no one value for the amount of force experienced, right? The force in my 3 examples is 0, 10, and 20 newtons. But what is the same, okay, and I guess I can write it even over here on the first one, 0 coulombs times the location in space has 10 newtons available per coulomb. So the common thread is that the location always offers up the same property, 10, but the charge we're placing there is different, therefore the force is different. Okay? So the key thing here is to understand that the location has a certain property. Then you have to still supply what are you going to put there before you know how much force it experiences, right? Does that make sense? So that you can see is an incredibly handy formula because when someone gives you the electric field, they've basically handed you, if there are 3 or 4 or 12 different charges in the neighborhood, that's the overall effect they have at this location, and that's the local condition. All you need to do is supply one last thing, which is what are you going to put there, and you have the force. Okay? Are there any questions on that so far? Okay, so that's the effect. So let's start kind of building out this whole thing. In fact, let's go ahead and start a chart where we have everything laid out. We have the cause over here, which is going to be big Q. We have what it affects, or the effect is going to be on little q. That's just the labeling scheme that we have. The cause is the electric field, and the effect will be a force. We need to talk about size and direction for both of them. We already have one of these 4 boxes filled in, so to speak. We have the size of the force, but we have to address the other 3 aspects. The direction of that force, and then of course also the size and direction of the electric field. So that's what we're going to start on here. And I do want to point out from the outset that whatever fancy scheme we come up here, this is just a different picture or perspective, so it cannot, of course, come up with a different answer than what we already know, which is that like charges repel and opposite charges attract, right? If we came up with something different, that would be a different answer from nature. If we want to think of the charge interaction in a different model, that's just for our benefit, right? It's still a fundamental experimental fact that things that are similar, like charges, repel, and things that are opposite charges attract. So we have to make sure to keep that in mind, okay? So remember that whatever we come up with here is going to have to be like charges repel and opposite charges attract. You can think of it as what we're basically doing here is taking this idea of like repel and opposites attract, and we're just cleaving it in half. Right? We want to be able to talk about the cause independently from the effect. So we want to be able to talk about each piece on its own because the electric field is the middleman. Question?
I don't think you provided everything on the screen there on your video.
Oh yeah, I know that app is, it doesn't show the whole screen that's actually getting recorded, but thank you. Well, fingers crossed anyway, that's how it works, I'm pretty sure. Okay, so let me go to the cause side. So there's got to be a better way to draw the electric field than some like soupy green mess which conveys no information other than it either is in a space or it's not, okay? So I'm going to suggest to you, and of course this is a convention, it's pretty much universally used, but it's just a convention. Instead of drawing it as just kind of a green blob, I'm going to draw it as a series of radial lines. That's my electric field. Now, of course, what you've mostly used arrows for are forces, and so you might mistakenly look at that and saying there's like 8 strings attached to the charge that's being pulled in different ways. That's not what's going on here. In fact, we can pretend this is the only charge in the universe, so there's nothing else to pull on. This is just our way of visualizing the influence it puts out into space. And of course, it's made by this charge. It can never act back on itself. Okay? This field is only eligible to act on other charges, and right now there aren't any. Okay? Now, Why do we choose it to draw it as a series of radial lines? Well, I'm going to show you that there's many advantages to that. Okay. I should also mention that, of course, it's everywhere. So this is just the sampling. You might say, if I'm here, is there no electric field? Well, of course there is. It's everywhere. But if I literally blacken the whole screen with radially outward arrows, then it's going to be a pain to draw, right? So you can't like sneak in between electric field lines, okay? There's electric field everywhere, and this is just kind of a sampling of what it looks like. Does that make sense? Okay, so we go ahead and draw it like this, but again, this is by convention. By convention. And from that, we can actually go ahead and start to fill in the size of the effect, or not only the size of the effect, but its direction as well. So, for instance, let me drop in another charge, plus q, little q. Now we, as the kind of omniscient viewer here, we can see both charges just fine, and we know that what's the direction of the force that will be felt on this little q? To the right, right? Because we know that light repels. If we instead dropped in a negative charge, well, we, in the force picture, know that opposites attract, right? So we know that the force on this particle relative to big Q will be which way? This way. So, if these two charges are really thinking locally, right? They have no like long view of it, right? They're not wearing their glasses or something like that. They can't see why it is that they're being pushed to the right or left. They're just reacting to the local field conditions. And here's something we've discovered. Positive charges feel a force along the field line, same direction, and negative charges feel a force opposite. Okay? So I'm going to suppose that the direction of a plus q feels a force with the field line, and the negative feels a force against the electric field line. This is the force we're talking about. So I like to affectionately say that the plus q's like to feel a force downstream, and the minus charges feel a force upstream. They're like the salmon charges, okay? So, in fact, I guess I can even go over here and draw a little picture of that. If the electric field at some local place is pointing to the right, plus charges feel a force that way, and negative charges feel a force opposite. Now notice that that is perfectly in agreement with like charges repel and opposite charges attract. In fact, that's how we got that, right? But it allows us to decouple what's causing the electric field, right? This electric field, which is pointing to the right, that's the local field we have. We might not have any idea why the field is that way, okay? But we know that if that's the local condition, then how positive charges and negative charges react when they're put there. So I guess over here we can also, going along with this, electric field lines point away from positive charges. So we can talk about what the big Q causes. The electric field lines go away from it. That's by convention. And then, of course, if the electric field lines are chosen to point away from plus charges, well, other plus charges want to get away, so they feel a force along that field line. Negative charges want to go towards it, so they feel a force against, right? So this is just all still coming up with the same exact results that we know, right? So, the question is this universal? Can I say this in all scenarios? Well, certainly you can imagine dropping a plus charge over here. Which direction is that going to feel a force? Up. You can say in the force picture it's because it's repelled from this other plus charge, or you can say local conditions, it just feels a force downstream to the local field, right? And same with a negative charge, etc., etc. So the only thing we really have to do now is to make sure that this holds when big Q, which is causing the field, to draw the field of that appropriately so that we can count on these same force conventions. Okay? Because remember, the local field, who knows what causes it? So let's see what we have to do. For a negative charge, we just simply have to agree to draw the electric field lines radially inward. So the electric field lines come in from infinity and terminate on the minus charge instead of starting at the charge and going outward to infinity. So if we're going to do that, let's make sure that everything is the same. We put in a positive little q. Which way does that feel a force?
To the left.
To the left. We can think of it as either in the force perspective, that opposite charges repel, or sorry, opposite charges attract, excuse me. Or in the field picture, it's of course senses that the local field there points to the left and it feels a force downstream to it, right? And likewise, if we drop in any point here, I don't know, let's make it right here. This is going to feel a force upstream to the field. Why? Well, in the force perspective, it's repelled from the other minus charge. In the field perspective, it senses the local field direction and feels a force in the opposite direction. So everything that we said about the forces is holding. And we're simply forced to remember that electric field lines point towards minus charges. So now we still have like repel and opposites attract, but we can talk about the cause, the electric field, separately. It points away from plus big Q and towards minus big Q. And we can talk about the effects separately. That, okay, so if you have an electric field at some location in space, and you put something there, positive charge, little q, will feel a force with it, negative against it. The final piece we have is to fill in, of course, the size of the electric field. So that's next to our business. Are there any questions on any of the direction stuff before I move on? Because the direction stuff is now all established. Okay, so let's do the size part. So we have that the force is equal to Q times E. That's the field picture. Well, that had better agree with our previous result, right? That had better agree with the force picture. Remember, these are just two different models for describing the same thing, so we can't get a different answer from the same situation. Well, we already know the force law there. It's called Coulomb's law. It looks like this. So we have K, and then our two charges, big Q, little q, and then their separation. So basically, we can just match up the different pieces. There's little q. There's little q. So the rest of it has to agree. This, the size of the electric field, must be equal to this. So we're done. So what is the size of the electric field? We put in the equation. So what is the influence that big Q puts onto space? Well, it's a couple different things that matter, right? It depends on how big the charge itself is. And then the other thing is how far out in space are you away from it, okay? But that's it, right? So it depends on what charge is making the field and how far are you away from, out in space, away from this charge. You can see that it does get weaker with distance, right? You can see that as r increases, the field gets weaker. Question?
I was going to say, in your picture there, the last one I suppose too, the little cues, are they having any effect on each other?
No, the question was, you know, should I be worried about these two? I'm pretending that I'm swapping them out,
Okay.
one then the other, so I'm just worried about their interaction with this, not with each other. You're right, if I simultaneously put them here, they would also have to interact with each other, but I'm not.
Okay.
You know, I just don't want to erase one of them before I put the next one down in case someone's still copying the last one. Okay, so this is my equation. So that we find is that, first of all, big charges will have a bigger influence, right, at a given distance, but no matter what the charge is, its influence in space is not constant. It dies with distance. The further away you go, the weaker it is. So if the electric field will be stronger right next to a charge, and it'll get gradually weaker as you get further away, which hopefully is not surprising, right? A charge, you most notice its presence close by, and then if you're really far away, that charge has a vanishing influence, right? So, this gives me the opportunity to show you why drawing or choosing to draw the electric field as a series of radial lines is actually very informative, because we know that the electric field here is stronger because you're closer, and we know that out here the electric field is weaker, right? The drawing of the lines as radial lines allows us to look at the line spacing as a proxy in your drawing for how strong the field is. Here the field close by is stronger and the lines are closer together, right? Here the field out here is weaker and the lines are further apart, right? And by the way, that's true for both the positive and the negative charges. Whether the lines are drawn radially outward or radially inward, the lines are closer together when you're near the charge, and they're further apart as you go far away. So I want to point out that as far as drawing goes, the line density is proportional to the field strength. This is an incredibly handy way to look at just a drawing, but get a lot of information from that drawing. Okay? If you look at a field drawing, you just have a map of the electric field, anytime you see the lines closer together, that visually tells you that the field there is stronger. Anytime the lines are further apart in the same drawing, you know the field there is weaker. Let me just try to convey to you how much information can be conveyed this way. Let's say that you get a complex electric field map. Maybe it looks like this. Something like this. So this is a map of the electric field in some region. Now, if you're wondering what in the world can cause something like that, well, don't worry about it, right? We're purely on the effect side. So some possibly very complicated configuration of charges could cause a location in space to have this field. We immediately look at this, and we see that even though the electric field is pointing to the right, all the way down the middle, the line spacing is changing, right? How close are the nearest neighbors? So let's draw in 3 points. A, B, C. I'm not putting particles there yet, I'm just labeling the points. Where is the electric field the strongest? C. Point C, because the lines are closest together. Where is it the weakest? B, right? So we can rank the strength of the electric fields. C is the strongest, A is the middle, and then B is the weakest, right? We just look at the drawing and we know that already. We don't have to be told any numbers, we just look at that. And so if we were, for instance, to drop a charge there, let's say we have a positive charge that we drop at point A. What is the direction of the force? It's with, remember, positive charges feel a force with the electric field, so it's to the right. So go ahead and draw that. That's the direction of the force. If I drop that same positive charge at point B, what's the direction of the force there? Same. So it feels a force with the field. Is it stronger or weaker force than the previous one? If it's assuming it's the same charge, how about the force? It's weaker, right? If we look at this equation over here, the Q hasn't changed. I'm assuming it's the same charge. But if it's a weaker field, it'll be a weaker force, right? At point B, the weakest field, because the line density here is the lowest, right? Remember that the field will be stronger if the lines are closer together. In point B, the lines are the furthest apart, right? So the neighboring lines are further apart. That indicates a weaker field. If I drop that same charge at point C, it would feel the strongest field, right? And let me drop in the same amount of charge but of the opposite sign, just to spice things up. So that's going to feel the strongest field, but which way? Like that. That feels a force opposite to the local field because it's a negative charge. So you can see that if we choose to draw electric field lines such that the line density has meaning, then they can convey a lot of information just from a simple picture. Okay? But the starting point of that is that we draw the electric field lines radially away from plus charges and radially towards minus charges, because if we draw them as a series of radial lines, then that automatically sets up the line density to be a proxy for electric field strength. Okay, are there any questions on that? Okay, so here we have the full deal, okay? It's all just like repel, opposites attract, just cleaved into a cause and an effect part that we can talk about separately. These relationships will become second nature by the time you finish your homework 1, hopefully, or at least by the exam. And you will have a chance to play around with this with an applet and really get your hands dirty, well, figuratively speaking, it's a computer applet, next week. So that's what the electric field hockey lab is. It's just to basically go through all these cases and make sure you understand and start to know these relationships and feel comfortable with them. All right, so with that in mind, we have it all out there. Let's use it. And this is my opportunity to not only give you more practice with vector addition, do some example problems that are very much like your homework, particularly the back half of your homework, which is a lot of it is in the field picture. But then also show you why electric field is very useful as a computational device. Okay, so I told you earlier that one of the biggest arguments for the electric field picture is that it makes calculations more straightforward. Or more, I guess I should say, you might not think they're more straightforward, but the answers are more generalized. So let me go ahead and do an example. I guess I'll do one example, which is in 1D, and then I'll sketch out at least a second example in 2 dimensions. So here's my example. I have a Q1 over here, and I have a, let's call it Q3. I could number them however I want. Maybe I just don't like the number 2, so I'm going to skip the 2. Okay. Let me give you the values. Q1 is going to be minus 2 microcoulombs, and Q3 is going to be minus 5. And I'm going to ask part A, what is the electric field at this point, P? This is point P. There's nothing there yet. Point P, the significance of it, I have to tell you where it is. Point P is going to be 0.5 meters away from this charge and 0.2 meters away from this charge. And my first question is going to be, find the electric field at point P. There's also going to be a follow-up question, part B, but I don't want to tell you what it is yet. Spoil surprise. All right, so let's do it. First of all, I like to label minus, minus, so I don't have to look at the list of numbers to know at least what the sign of the charge is. And so here's what I have. I have a minus charge, and a minus charge everywhere in space contributes towards it, right? Electric field goes towards it. So I can draw this series of radial lines inward, 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 everywhere, but I don't care about everywhere, I care about point P, right? So what would be, at point P, what would point inward to this one? To the left. So I'll call that E1. If it helps you, you can draw it on the side here somewhere for your reference that if it's a minus charge, it goes radially inward everywhere. But we don't care about everywhere. We care about the point right about there. And that's why the electric field goes to the left at my point in question. Okay? All right, Q3, same deal, right? Q3 is a negative charge, so the electric field goes radially inward everywhere in space. But at point P, which way is that? To the right. So that would be, I'll call that E3 because it's by charge 3. And again, I don't want to clutter my diagram by drawing it radially inward everywhere, even points I don't care about. But if it helps you, it's a negative charge, and we're getting that piece of the electric field. Okay. So here we get to something, there's a fancy word for this, it's called the principle of superposition. That's not really necessary, but if you can hear the nomenclature sometimes. It basically says that the overall electric field at point P will be the vector sum of all the charges in the neighborhood. Okay, I'll write down the principle of superposition. All it simply says is that what actually happens at that point in space is a result of all of the influences, right? You can't cherry pick which charge matters and which one doesn't. They all matter, okay? All right, so vector addition, this is one-dimensional, so vector addition in one dimension is really easy. You basically have a plus direction, a minus direction. I'll go ahead and set this to be the plus direction, as you might probably guess, why not? And then electric field at point P will be plus E3 and minus E1. So I've put in the directions there. The direction is plus on that one, minus on that one. And then, of course, I'm just going to fill in the magnitude. Don't want another negative or positive to creep in there. I've already taken care of the directions. Those are done. I just want the number. So I go ahead and I put in the formula KQ3 over R3 squared and KQ Q1 over R1 squared. And then, again, you can thank the fact that there's absolute value signs in there for the fact that only a number will be supplied because I already took care of the directions, don't want an extra sign mucking me up. Okay? All right, so let's go ahead and do it. First of all, I have both charges. Make sure you convert them into coulombs before you put them in. So, and then the other thing I just have to identify is not only what are the influences to point P, but how far are you away from each influence at point P. So for Q1, let's say, we have to identify how far are we away from charge 1. What do I put in there? 0.5, right? I'm 0.5 meters away from charge 1. So the influences at point P is not as strong as if you were closer, but it's not as weak as if you were further away. You're 0.5 meters away from charge 1, and that sets the strength of influence that this charge has at point P. Likewise, you can see R3 is, of course, going to be 0.2. So you plug all that in, and you just get a number, and I'll tell you what that number is. That number is 1.053 times 10 to the 6th newtons per coulomb. So at this point, again, this empty point in space, there's nothing here, but because of the neighborhood, because there are other charges nearby, you can get 1.053 times 10 to the 6th newtons acting per coulomb should you decide to place it there, although we, of course, haven't placed anything there yet. That's what part B is for, by the way. I'm going to now put something there. But that's how much force you would feel per coulomb should you just decide to put anything there, just simply because of where that location is. It is not all by itself. There are charges in the vicinity, and there's an influence, a property that they put at the point P that is ready to act at anything that we may choose to place there. Okay? You might say this seems like a lot of force, 1,000,000 newtons. Well, 1,000,000 newtons per coulomb. You get 1,000,000 newtons per coulomb. Remember, a coulomb is a hell of a lot of charge. So chances are you're not going to put a coulomb there in any realistic situation. In fact, I'm going to now place a Q equals positive 10 microcoulomb charge there. Okay? So let's use our equation. Now that we're actually putting something there, that thing will feel a force. So we'll take the absolute value there, not that it matters too much because it's a positive charge, but you always want to remember if it's a negative charge. So that's how much charge we place at this location where the local neighborhood dictates that this much force is available per coulomb. It's like what we were doing earlier. The coulombs cancel. Also notice that the 10 to the 6th goes away with the 10 to the minus 6th. And we get a very reasonable 10.53 newtons of force that will be felt. So we found that at point P, the electric field was this. Oh, and I forgot, I should have written explicitly. It is a plus. So if it ends up plus, what does that mean? It points to the right. The electric field at point P points to the right. Now we just found that if we dropped a plus Q of that much, it'll feel this amount of force, and which way will it be, by the way? To the right. Positive charges feel a force with the field. Okay? So if we wanted to, for instance, make it a full vector, we might say the electric force is 10.53 newtons to the right. That's the most generic way of stating it, right? Because it doesn't force your positive axis choice on somebody else. Or if you were sure that someone else also thought that to the right was positive, you could maybe just say plus 10.53 newtons, and then they know the plus meant to the right. Now, if this sounds vaguely familiar, this is the exact same example I did last lecture in the force picture. In the force picture, I started with a charge here, and I asked what's the force on it. I skipped straight to part B, right? That's if you're wondering why I skipped the numbering, Q1 went straight to Q3, it's because this was the former Q2 that I put back, right? That's why there was a number missing. And I got this exact same answer, right? So this is the same answer ultimately as the 1D example for the force picture. I purposely redid the same example that I did before. Except here's the thing. My answer before was only good for the charge that I placed here. And so that was something that I committed to from the very beginning, what charge was going to be there. Now that I've prepped part A and I know about this location, I've basically done the heavy lifting of figuring out what's going on there because the charges Q1 and Q3. I can give you a list of 17 different charges to swap in and out of point P, and you can very quickly tell me what happens to them. So let me give you an example. Let's say I take part C, and I instead place a Q equals minus 5 microcoulombs at point P, and ask what's the force there. Well, I can very quickly do that. So I do the same exact thing, same exact formula. It's exactly the same field, right? So I'm putting now a different charge. Remember to take the absolute value of it. And I'm putting it into this location, which has exactly the same property. And finding the force on that particle, this completely different particle that I've swapped out, is just as quick as multiplying the new charge by the field at this location. That is the computational usefulness of the field, because once you find the field at a given point, that's a property of the point that doesn't change depending on what you put there, or maybe you don't put anything there. That's the very practical nuts and bolts usefulness of the field picture, is you get to find out about a location without having to commit to what you're going to put there. You find out about the location, you get this number, you multiply by what particular thing you feel like putting there, and it'll very quickly tell you what that will be. In fact, in this case, again, the coulombs cancel, the 10 to the minus 6 and 10 to the 6 cancel. And if I can just quickly look at the situation, well, I know that I'm putting half the charge there, right? If I'm putting half the charge, it used to be 10, now it's 5. So half the charge in the same field means what about the force? Half the force. So let's see if I can divide 10.53 in half. That's 5.26, 7, something. Is that right? Yeah. All right. So that's how much force that particle feels. Right? That's how fast it is. You just take the field, multiply by the new charge that you swap out, and you get your new force. I guess I'll write that. So it's half the little q in the same field. That's half the force. And of course, the other thing we should note, that's just the size of the force. What's the direction? To the left, right? So if we put a point P, it has an electric field pointing to the right. If we put a negative charge there, it'll feel a force to the left. So you should, if we wanted to properly state the entire force, we might say the force is of size 5.27 newtons, and the direction is to the left. That'd be the most generic way of stating the direction without forcing your plus axis choice on somebody that they didn't know. Or if you were sure that what they considered to the left was negative, you could just say the force was negative 5.27 newtons. So that's pretty much it. That's the idea of executing in practice one of these things, okay? Are there any questions on that before I do a two-dimensional version, at least sketch it out? Okay, so I'm not going to do the whole thing, I'm just going to sketch it out. Same ideas as before. And you guys will have a bunch of these kind of things on your homework. So my example 2, which is in 2 dimensions, I'll go ahead and put 3 charges along a square, but I will of course omit the charge on the 4th corner. That'll be my point P. So this is following along the same lines I did last time. In the force picture, I did a problem with four charges, each on a corner of a square, and I asked what's the force on one of them. I'm just going to sketch out what you would do if you decided to do it in the field picture, which is that you take out the charge of interest, you calculate the field at point P, and then you can put the charge that you want back. So let me remind you how this went. Our labeling scheme was, let me make sure I number them the same. Q1, Q3, and Q4. I guess I'll give you the amounts of charge just in case you don't have them handy. Plus 10 microcoulombs, plus 6, and minus 3. And they've all been obviously labeled capital Q because they're going to be things that I more care about the cause of at point P than anything else. So let's just sketch it out. Let me label each of these charges, at least if they're plus or minus, so it can help me not have to refer to my number list the whole time. All right, let's start with Q1. What is going to be the direction of the electric field contributed by Q1 at point P? To the right. Okay, so for those of you that didn't see that, let's make sure you do. So remember that a positive charge contributes radially away in every direction. Okay, so if you want, you can draw it off to the side here. Positive charge contributes radially away. Well, we don't have to draw it everywhere. We're right about there, so we're getting a rightward field, right? Contribute at point P. Okay, how about, let's skip to Q4. Which way does Q4 contribute a field at point P?
Down.
Downward, right? Because it's ever radially toward everywhere, and radially towards is downward. Okay, then Q3, that's a positive charge, so it contributes radially away in all directions, so it would be like that. We're positive charge, but we're catching this little bit of field. So, looks like this. So, if we want to find the overall electric field at point P, we once again have to do the vector addition. And this is, of course, going to involve some SOHCAHTOA, right? We're going to have to work out the x direction and the y direction separately. What I would do if I were you, I'd probably use your standard x and y axes. Then electric field 1 is entirely on the plus x direction. Electric field 4 is entirely on the minus y direction, and only E3 would need some SOHCAHTOA business, because it contributes both in the plus x and plus y, right? and so on and so forth. The idea is the same, the math required to execute on the answer is just a little bit more challenging, right? So you have to do all your x components lined up, your y components lined up, you get the x and y components of the electric field, you put them back together with Pythagorean theorem, inverse tangent, right? So let me just tell you what the final answer is. Try it yourself at home if you like, if you want a warm-up problem before you do the homework where you know what the answer is. The electric field at point P ends up being roughly 1.22 times 10 to the 8th newtons per coulomb. And then the direction, of course, is now going to be a little bit more complex than just right or left. It's actually going to be 4 degrees clockwise from the plus x-axis that I used. By the way, for those of you that may not be accustomed to me from Physics 1, I generally don't bother with angles greater than 90 degrees. Okay, so I'll usually give it from a nearby axis. In this case, it's the plus x-axis. But if something is like 3 degrees from the minus x-axis, I'm going to say 3 degrees from that, not 177 or whatever from some other faraway axis, right? So I try to keep the angles between 0 and 90 degrees and just express it from a nearby axis, even if it's like the negative x or the negative y. So what does it look like? It looks something like this. Actually, let me not even bother to do a new diagram. Let me just draw it in here. This is the electric field at point P, something like this. It's 4 degrees from here. And that's the strength. Was there a question somewhere? Yeah?
What's the distance between?
Oh, sorry, yes, I forgot to give that. It's the same problem as last time, so it'll be 3 centimeters and 3 centimeters, right? Is a square. So that's the idea. And once you know the electric field at point P, now you know everything you need to know about what neighborhood it lives in, you can start swapping out charges, right? So now that you know the electric field at point P looks like this, you can stick in a positive Q. Which way is that going to feel a force? With it, right? So that'll also feel a force 4 degrees clockwise from the plus x-axis, right? If it were a negative charge instead, it would feel a force opposite, so that'd be 4 degrees from the minus x-axis. And of course, depending on the amount of charge, that would tell you the amount of force, right? So one of the things that I would do if I were you, I'd put the same Q2 back that used to be there in the last one. Make sure that once you found your field and multiplied it by that force, so you have this, put back the same charge as previously, same as the last example in 2D, and then of course make sure that the force comes out to be the same. Of course, in the force picture, we always jump straight to the force. The electric field picture is nice because it gives us a nice plateau or to stop, and then we can build on that if we are interested also in the effect and not just the cause. Okay, so if we're not only interested in point P, but also in placing then something at point P to feel an effect. And I should mention that many of the homework problems deal only on the cause side or only on the effect side, right? For instance, only on the cause side, I'd stop with asking what's the electric field at point P. I wouldn't bother to put a charge there because we're focusing on the cause side, right? Sometimes I'll just ask about the effect. I'll just hand you the electric field. You don't have to find it yourself. You just have to calculate the force on something that you put there. So it gives me the freedom to not just have you do the whole problem straight through, cause, find the cause, then find the effect. I can just ask on the cause side or just ask on the effect side. And you'll find there are several homework problems of each variety. Okay, are there any questions on this? Okay, so The next order of business, and the final thing to close out homework number 1, is I want to take a step back, see the forest for the trees. You notice that in these problems, this one and the one I did right before it, I very specifically picked one point that I'm going to focus in on and find very, very carefully both the exact size and exact direction of the field. Sometimes you don't want to focus in on one tree. Sometimes you want to see the whole forest. So sometimes what you want to do is you want to get a sense of what does the electric field look like everywhere. Now obviously you're going to have to give up on the precision of exact numbers, but sometimes you just want to kind of get a sense of the whole picture. So the next thing we're going to talk about is just generally drawing electric field maps. So let's talk about drawing electric field maps. So again, this is less quantitative. We're not going to focus in on these specific numbers, but certainly way more locations where we're interested in knowing it. And I think the best way to do this is by example. So I can kind of show you the tips and tricks along the way of how to do this. So my charge configuration that I'm going to draw is a very important charge configuration. 2 equal and opposite charges. Okay? This charge configuration even gets a name. It's called an electric dipole. In chemistry, this is a very important thing. Electric dipole is basically 2 equal and opposite charges with some separation. Okay? And so my goal in this situation is not to pick one point and do an exact calculation. I want to sketch the electric field line, the electric field everywhere here. Okay? And I just want to get a general sense of which way it points. So in order to do that, what I'm going to do is kind of just think through it. First of all, let me label the charge on the left, the positive charge, with red. And let me label the one that's negative on the right here with green, just so that I can get a general sense of keeping track of what's going on. If you have some different colored pens, or maybe just a pen and a pencil, that would be great. You might want to put in your notes the same way. So I'm going to draw their individual field lines. Positive charge points radially away. And I'm going to do it with dotted lines because, of course, both charges matter, so one of them alone is not going to be the whole thing. So there's my positive charge with its own field lines pointing radially away everywhere. I'm going to deal with the negative charge, points radially towards it everywhere. Like so. And then, what I need to do is somehow figure out how to get my head around the fact that the net electric field at any given location is actually the sum of the two. So, that's where I'll start off next time. I'll see if I can use certain tricks to figure out kind of a general pattern that might be seen for what will be the vector sum of the red line and the red line and the green line at every point in space. So I'll do that next time, and that will be I think the last thing you need for homework 1.